Hello, it's Keith here, and this is lesson 14 of the YQuest series of my Z80 assembly programming tutorials. Now we're back on the MSX1 today. Before we had a look at it and we were creating the graphics with the tile map, we're going to extend them and we're going to add hardware sprites to the mix. This is going to make the game movement a little bit smoother. Let's just see it in action. If I just fire this up here. So here's the MSX1 version, and if I figure out the controls, you can now see the main Y and the bullets are now able to move more smoothly. There's not the limitation of an 8x8 grid anymore. Now you'll notice the enemies are still moving on an 8x8 grid. They're still being drawn with the tile map the way this is set up. The reason for that is the MSX1 is only capable of 32 sprites and the object array is 40 sprites, so there weren't enough spare sprites. But anyway, we've got this set up. We're going to go over the code today and learn about how to get hardware sprites working and what I've done to tweak the game to get it working as quickly as possible. Let's go over to the code and have a look. Okay, so what's changed? Well, first of all, there's been some changes to the common code since last time we saw this. There is now the spare byte of the object array is the hardware sprite number. If this is 0, then the sprite is being drawn with the tile map as before. If it's non-zero, then we're using the hardware sprites, and the number of the hardware sprite is defined by that. You see, the system, we need to define each hardware sprite as doing a different job. So hardware sprite 1 could be the player, hardware sprite 2 could be a player bullet, hardware sprite 3 could also be a player bullet. But if we use the same sprite for the bullet and the player, then you'd find they'd flicker on and off, or one would never show or something. So you need to allocate a hardware sprite number to each object that's visible on the screen. So we're using that H sprite number with the spare byte of the object array definitions. And then in our common code, we're going to use that when we're drawing. Here you can see the draw object routine, and at the bottom of this we're checking what the value is, and basically if the value is under 128, it's considered to be potentially a hardware sprite. If it's 255 or 0, those are the uninitialized values of main data and also the bullet array, then it's considered to be a tile map object. So you can see here we're using this doGetHSprite object for the hardware sprite and the doGetSprite object for the regular tile-based objects. So that has been changed there, and we also have a new function here for defining the sprite numbers that are going to be used by the objects. Set hardware sprites will take an IX object, a count and a sprite number, and it will sequentially set the hardware sprite numbers of consecutive objects, and that is allowing us to set up the objects quickly during the initialization routine. So that's what we're going to be using there. Okay, so that's the common code changes. Not very much, you'll see. The rest of the changes are in the platform specific code. Now I've disabled the collision masks because now we've got nice smooth movement. And the first thing you will see is we actually need to reinitialize the sprite data. We've got it once in the tile map patterns, but the hardware sprites use different pattern data on the MSX1, and that pattern data goes at hexadecimal 3800 here. Now coincidentally, there's enough data area for 64 definitions, and that's exactly how many I'm using in my game, so I was very lucky there. It's beneficial having a very simple game sometimes. So we're transferring just the sprite data to this memory address. Remember, we were transferring all the bitmap data before, which includes the font. The font's not being transferred this time. And so that's the first thing we're doing there. Now, when the level starts, we're defining each of the object sprites, so that we're setting the hardware sprite to number 1 for the player object, and then we're using that set hardware sprite to define the sprites for the bullets and the enemy bullets. Now that leaves a few spare sprites, so we can actually define part of the object array to use hardware sprites if we wish. If I just fire this up now, well, you can see now that the enemies are moving. You can see they've also lost their colors though, and the reason for this is I haven't defined the palettes properly, so maybe not the best way of doing things there. Now I've decided at the moment to just use the tile map for all of the enemy graphics and the hardware sprites for all the player graphics and the bullets. But as I say, if you preferred to do it differently, you could change the code and use those extra hardware sprites when the game proceeds to the later levels that have a lot of objects on screen. Because of the way the game's coded, the objects that don't have a hardware sprite allocated to them will of course draw with the old tile map code, so it does work. It's perfectly possible to do that. So that's defining the hardware sprites that are going to be used. This code has not changed in any way. It's all exactly the same. Now, doGetSprite object here hasn't changed either. What has changed though is the blank sprite object routine. You can see here now we're checking again to see if we're using a software sprite or a hardware sprite. And the hardware sprite routine is going to end up running this code here. Now this code was being used before, if you remember, by the multi-platform code Where is it? Here it is. This doGetHSprite object is the equivalent of the old doGetSprite object for hardware sprites. So we're loading in the sprite frame as before, multiplying it by 16 here to get the effective sprite bank number, and then we're adding the sprite number to that. Now we're no longer adding 96 because the patterns we're using now don't have any font included. And we're also loading in a byte of a palette. Where's that palette? It's down here. So these are the palettes for the sprites. There's one color for each sprite. Ironically, say the Tarmap uses 2 colors for each line, whereas the sprites just use 1 color per sprite. So those are the colors for the sprites, and we can change those and change the color of our object. So we're loading that in, and we're storing it in L here. We're getting the X and Y position. Now before we were having to sort of shift these down to an 8x8 grid, we're now actually having to double the X position because the definition of the internal calculations is actually too low resolution now. So it was designed for a 320 pixel widescreen, so it worked from 0 to 160, whereas now we're using a 256 pixel widescreen, and we can move at the pixel level, but the internal calculations aren't high enough resolution for that. So we're multiplying it up by doing a shift of the X position, and then we're using set hardware sprite to do the work of setting the sprite. So this is the bit that you would want to look at if you're going to borrow this code for your own program, which of course I totally encourage you to do. So each sprite definition within VRAM uses 4 bytes, and the definitions start from 1B00. And so to select a hardware sprite number, we multiply the hardware sprite number by 4 and add that to 1B00. And that's basically what we're doing here. So that's selecting the address. Then we write the Y position as a byte to VDP data. Of course, set write address is selecting the VDP VRAM address. We've used that many times before. So we're selecting the Y address here. We're setting the X address here. The pattern number here within that sprite VRAM, remember it's a different address, and here is the color and other options here. So we're just loading in from L here, which we defined as the color from the palette there. And that's really all there is to it. As I say, the last thing is just this bit here. Now you'll notice here that there's really not many changes at all. I think there was an extra option enabling here to turn on the hardware sprites maybe, but generally speaking there's not really much change at all. So yes, it was pretty easy to add hardware sprites to these games actually. So hopefully it's going to be interesting to you. So that's the MSX1 version there. Of course, as always, you can go ahead and download the source code for today's example, and as I said before, use it in your own source code, in your own games. You don't need to give me credit, I really don't care. I just hope you find some use to it. So there we go. Anyway, I hope you've liked this. If you have, please like and subscribe and all that kind of nice stuff, because that really helps me out. If you like the videos, YouTube might recommend them more, and if you subscribe, it gives me a little bit of motivation to keep working on it, because it takes a lot of work, obviously, you can probably guess. So anyway, whatever you do though, I hope you enjoy your MSX1. I hope you have all the best of luck with your own programming projects. I wish you all the success with them. So take care of yourselves, and goodbye.